In this video, we're going to try and determine whether or not this series will converge or if it will diverge. So going back to our theorem, it requires the function to be continuous, positive, and decreasing. Our function here is not decreasing. Our function here is increasing, and then it decreases. So we might have to cut up somewhere around here. Set our capital N to be here, or we might have to cut up somewhere around here, set our capital N to be around here. But we require the function to always be decreasing. So the reason why we can see that we need to cut up around here is because in a way we cheated by having the luxury of drawing this graph. But in reality, you only be given this. You won't be given a graph. So in reality, you only be given this. So you've got to check that it's always decreasing. The way you do that is to map a function on top of this sequence. So look at the function and then differentiate the function. Then you can check that it's always decreasing. But let's start all over again. When given something like this, the first thing you need to do, the first thing in your checklist, is to make sure that as n tends to infinity, make sure that this sequence heads towards 0. Suppose this sequence heads towards something other than 0. Let's say suppose the limit heads towards 3. Then as you're summing up everything from the first term to infinity, you're always going to add 3 to this. You're going to add another 3. You're going to add another 3. So if it doesn't converge to 0, let's say it converges to 3, then you're always adding more and more to the sum. So it means that it's going to diverge. So the first thing you should do is make sure that this limit heads towards 0. If it heads towards anything other than 0, then you're going to add more and more and more to the whole summation. So it's just going to get bigger and bigger. So first thing, make sure it heads towards 0. So maybe use L'Hopital's rule as take the limit as n tends to infinity. So take the limit of this as n tends to infinity. Here you've got infinity over infinity. Use L'Hopital's rule to determine that. Make sure that it heads towards 0, basically. And we've done this many times. So you should be able to, by now, check that that it heads towards 0. So now we need to check that it's always decreasing. So we would map a function on top of this series and then differentiate it so we can get an idea of the gradient. We need to make sure that it's always decreasing. So map a function on top of this series and then differentiate it. So from here, differentiate it, use a quotient rule. So square this, blah blah blah, differentiate it. It will then give you this. Tidy up, and then it will then give you this. So now when we'll we require the function to be decreasing, meaning we require f prime to be negative because it's going downhill. We require this to be negative. So when will this be negative? When will this be negative? So let's just set it to 0. Times both sides by x squared. So that will then give you this. So when will this be 0? Well, it would be 0. This is quite easy to do. So you times both sides by x squared, and then that will then give you natural log of x equals 1. So exponentiate equally to both sides. So x equals, well, you see, when x equals e, the gradient will be 0. Now beyond e is the gradient. Let's look at this. Hang on. We started out with the function. Differentiate it. It gave us this. Tidy up. It then gave us this. And then looking at this, when will this be negative? Well, this thing here will always be positive because you're squaring a number, so it's always going to be positive. So it boils down to when will this be negative? Well, this will be negative when this is bigger than 1. Well, if you look at the natural log, this is 1 here. Well, log e will be 1. Log e here will be 1. So beyond e, this thing here will be bigger than 1. So anything beyond here the f prime will be negative. So looking back at this, beyond e, the gradient will always be going downhill beyond e. So hang on. So going back to here, hang on, bear with me. So beyond e, so e is around about 2.7, around there. So beyond e, we know that the gradient will be negative, meaning that the function is going downhill. So yeah, so everything here is satisfied. So we should set our capital N. Bear with me. We should set our capital N to be well. Capital N can only be an integer. E, beyond e here, we know it's going downhill, so we can set up anywhere beyond e. So let's just set capital N to be at 3. So going back to here, if we set capital N, sorry, bear with me. If we set capital N to be 3, if we set capital N to be 3, then everything here is satisfied. It's continuous, that's good. It's positive, that's good. Now it's definitely decreasing because the gradient beyond e, the gradient is always negative. I will continue in the next video. So now we can compare. Hang on. Now that we know everything's been satisfied, we can start to compare this with this. I will continue in the next video.